In this video, we're going to look at the connections between integration and inverse trig functions. We're not looking at integrating trig functions in this video. That's been another video on that. But we are looking at when functions integrate to inverse trig functions. So we've already learned that the derivative of arc sine x is 1 over root 1 minus x squared. So already we know that the integral of 1 over root 1 minus x squared is arc sine x plus c. We therefore know by the chain rule that if we have y equals arc sine of ax, that is going to differentiate to a over 1 minus ax all squared. So again, we have something which integrates to arc sine ax. Now, a very useful result, which is often used but it's also given to you in the formula book, is, well, let's actually derive it. If you start not with arc sine x, but arc sine of x over a, let's see what we get. Well, dy by dx by the chain rule is going to be 1 over root 1 minus this squared, multiplied by the derivative of this. So the derivative of this is 1 over a, and that's all over root 1 minus x over a all squared. Now we can actually neaten this up a little bit. If we multiply top and bottom of this fraction by a, what do we get? Well, we get 1 on the top. Now, multiplying the bottom by a, we could bring that into this square root as a squared. So we have the square root of a squared minus, well, x squared over a squared times a squared is just x squared. So here's a really useful one. If dy by dx is anything in the form 1 over root a squared minus x squared, well, its integral, well, the original function was arc sine of x over a. And so this is a result given to you in your formula book. We can integrate anything in this form directly to arc sine of x over a. Of course, there is a restriction here on the x terms because we've got the square root of a squared minus x squared. X squared must be between minus a and a, otherwise we end up rooting a negative there. So we do have this thing which, well, we could say the modulus of x needs to be strictly less than a. So if a is like 5, x can be between but not equal to minus 5 and 5. That guarantees we're not rooting a negative or a 0, or we're not dividing by a 0. Okay, let's do a similar trick for arctan as well. By the chain rule, this is the derivative of this, 1 over a, divided by 1 plus this thing squared. And this one's a little bit more straightforward. You can simply multiply top and bottom here by a squared in this case. That gives you a on the top, and it gives you a squared plus x squared here. So once again, we have a result where if we find anything in this form, this can integrate directly to arctan x over a. Notice in this case there's no restrictions. The function arctan exists for all values of x, and this is fine for all values of x as well. Now, you'll usually see this one presented not with the a here, but in fact both of these divided through by a. What I mean by that is we've just established that the integral of a over a squared plus x squared dx is arctan of x over a plus c. But generally you'll see it written like this: the integral of 1 over a squared plus x squared dx is 1 over a arctan x over a. All I've done there is divide both sides by a. And that's just to give it a bit more symmetry with the arc sine version. Here's a summary. We have the integral of 1 over root a squared minus x squared is arc sine x over a plus c. And then the integral of 1, again, over not square rooted, just a squared plus x squared, is 1 over a arctan x over a plus c. And there's that restriction there on the arc sine version. Should also point out that there is a restriction on a. A does have to be positive. And the reason why it has to be positive is if it's, or rather we treat it as positive because it's a square there anyway. So like if you saw the square root of 9 minus x, we're assuming that 9 is positive 3 and not negative 3, because that gives us the correct value inside here. Otherwise, you end up with the negative of what you should. So a is treated as positive, and x has to be between minus a and a. Okay, you may have spotted that one of the functions is missing. So, does anything integrate to arc cos? Well, it should, because we did differentiate arc cos, and recall that the derivative of arc cos, well, it was minus 1 over root 1 minus x squared. So that integrates to arc cos, right? Well, kind of, but actually we've got an interesting little reason why we don't use it. Consider the fact, and what I've got here, by the way, is a plot where the purple curve is arc sine x, and the red curve is arc cos x. Now notice that these are just transformations of one another. In fact, the full transformation is that arc cos of x, so the red curve, is just minus arc sine of x, so this purple one flipped upside down and then shifted up by pi over 2. Well, the implications of that is that anything that does integrate to arc cos, we could just express it as some transformation of arc sine. In fact, the pi over 2 bit is completely disguised, because anytime you do an integral, there's always a plus c anyway, which eliminates that. And so if you ever think that you have something integrating to arc cos, we can just say it integrates to minus arc sine x, and then the plus c captures that pi over 2. So it just reduces the number of formulae we need to remember. So basically, if you're integrating something to do with inverse trig, it's typically either arc tan or some transformation, or arc sine. So in conclusion, these are the two results you need to know. They are in your formula booklet, so feel free to use them, and in the next video we will go ahead and do that.